Hi, I am Gust, and on behalf of VU, Sumit, and myself, I will talk about how we integrate language models in programming by example. First, let's meet Flashfield. This little button helps millions of users to automate repetitive tasks. It does so by learning a small program that performs this task for them. But wait, computers learning how to program themselves. Is this how AI is taking over the world? Not really. It seems like Flashfield knows how to do structural transformations, but it doesn't really know what exactly it's working with. Let's try another one of those technologies that's ready to take over the world, GPT-3. GPT-3 is what we call an autoregressive language model. This means that given a piece of text, it returns a distribution over the most likely token to follow this piece of text. We can then add one of the most likely continuations to this input and repeat the process. By repeatedly predicting continuations and adding them to the input, the language model is effectively able to generate text. But that is not all. If we encode an example of a task in a smart way, GPT-3 will respond with a distribution over the answers of this task. Instead of fine-tuning, the model is capable of few-shot learning from examples encoded in the input prompt. This is what we call in-context learning. Because it has seen a lot of text, GPT-3 can act like it knows what it's talking about and solve the kinds of problems that Flashfield struggles with. Even more, GPT-3 can perform tasks that are very similar to Flashfield, like the converse of the previous task, concatenating a constant to a property of the input, or a combination of these tasks. And this brings us to an interesting question. Can't we just replace Flashfield with GPT-3? But we cannot. Some tasks are trivial for Flashfield, but hard or even impossible for GPT-3. For example, it struggles with extracting a constant number of characters because of how it tokenizes text. It also struggles with complex substring extraction, for example, extracting the last directory from a path. Let's try the other way. Can't we just extend Flashfield to solve problems involving semantics? In order to do so, we first need to roughly know how Flashfield works. In short, Flashfield learns programs that build the output piece by piece. The programs are learned over a domain-specific language, or DSL, which is a context-free grammar that describes the syntax of allowed programs. Learning is done through deductive backpropagation. Let's briefly show how that works. Say we are given a problem of mapping 1 to row 1 and a DSL. We choose one of the allowed production rules, in this case it is the top-level concatenation operator, and look at its first argument. We then ask what this first argument can be in order to generate the desired output. In other words, what can O be to generate row underscore 1? There are 4 things that we concatenate something else to generate row underscore 1, which is R, RO, row, or row underscore. We pick one of these, row underscore, and then try to figure out how we can build this string. We follow an allowed production rule and arrive at a substring operator. Again, we ask the question what its arguments can be to generate row underscore. But there are no positions in the input string such that row underscore is a substring, so we reach a dead end. For one of the other allowed production rules, const string, there is a value for its argument that can build row underscore, namely the string row underscore. We then go back to the concat statement, for which we have now been able to build the first argument, and try to figure out what its second argument can be. So what can we concatenate to row underscore to build row underscore 1? Indeed, a 1. And 1 can be easily obtained by taking a substring that is the whole input. Essentially, deductive backpropagation recursively breaks down the problem into smaller subproblems until each of these subproblems can be solved. Typically, there will be many solutions for the subproblems, which can be combined to yield even more solutions for the entire problem. All of these solutions are then ranked by some heuristic on which could be the desired program. For example, taking the whole input is more general than taking only the first character, which is simpler than a program with more concatenations. Given programs that require semantics and a starter DSL, we can then simply add some new operations. In this example, we add operators to convert strings to numbers and vice versa. But then we get new languages and require a new, pretty complex operator. And then we get some more operations for dates. And as we encounter different problems, more and more operations are required. Obviously, we can't just keep adding more and more operators to the DSL. Instead, we propose to combine both of these powerful and popular technologies, letting each one do what they do best. Flashfield is tasked with breaking down the problem into smaller subproblems, like figuring out that we need to concatenate a constant to the result of some other function. We then use GPT-3 to solve the subproblems that Flashfield cannot solve on its own. In other words, we use GPT-3 to learn this anonymous function from the few examples that are provided. Substituting I in the prompt with 2 in the prompt and picking the most likely answer that GPT-3 returns, Flashfield can then build the correct output. In order to let Flashfield delegate tasks to GPT-3, we introduced semantic operators, which are essentially GPT-3-powered functions. The first one is a string-to-string function called semmap that looks up properties of the input string using the closed-book question-answering capabilities of GPT-3. The key information required by this semantic operator, the examples of the task to show to GPT-3, is encapsulated as an argument. This allows the synthesizer to effectively learn the operator on the fly using deductive backpropagation. We then need to know two things about these arguments or operators. First, how do they get the result? And second, how do we learn them? Let's start with the first one. Each time the semantic operator is called, both the query and the input are used to build the prompt. The query describes some examples of a question answering task, and we then ask the same question about the input. After calling GPT-3, the most likely answer is always chosen. Next, let's see how this argument can be learned. After breaking down the problem, the question arises of which query maps 1 to 1 and 2 to 2. The answer is pretty straightforward. But the idea behind this answer is actually quite nifty. We're essentially considering GPT-3 to be an oracle that can solve any problem thrown at it. We will later use ranking to decide which of the programs actually need this semantic operator. Let's look at the second operator. Access to GPT-3 allows us to work with natural language inputs, like in the pictured example, where the goal is to add markup around the predicate in a sentence. This cannot be achieved efficiently by the semantic map. Instead, it would be way more helpful if we could obtain the positions on the left and right side of the predicate. We can use these positions to partition the input and insert constants where applicable. This is done through a semantic position operator. So, how does this position operator work? Again, the query parameter and input are used to build a prompt for GPT-3. The prompt is executed and the response is recorded. It is converted to an integer by looking up its position in the input string and returning either its left or its right side, depending on the direction argument. When learning the query for a semantic position, we already know that we need to take some substring and are asked to figure out one of the positions of this substring. We pick a direction and then ask what the query can be such that position 2 is on its left side. All combinations of words that start on the right side of this position could then be the ones we are interested in. In this case, love or love pizza. Again, ranking will allow us to pick the correct one. We conceptualized a third matching operator that maps a string to a boolean, which can be used in top-level conditions, but I will not go into detail about this. Shown in black is a simplified Flashfield DSL, and in red we show the new operators, each of which integrates with a different level of the DSL and exploits a different ability of GPT-3. Semantic matching in the top-level condition uses classification abilities. The semantic map string expression uses the closed-book question-answering capabilities, and the semantic position operator uses the natural language understanding capabilities of GPT-3. With the DSL, semantics, and learning out of the way, we can get to ranking. On top of the actually desired program, both semmap and sempos will yield a lot of redundant and trivial candidate solutions, and we use ranking to select the most likely desired one. First, we rank the programs as Flashfield normally would, making the semantic operators free for it to use. And we re-rank it based on the properties of the semantic operators. First, we punish requiring more characters in semantic operators. For example, requiring only 2 characters on the left is better than requiring 6 on the right. Finally, we punish requiring more unique queries to GPT-3, where obtaining the left and the right side of the same word receives a higher score or less punishment than taking different combinations. We have a language with new operators and ranked programs, so we should be go to implement our semantic program synthesizer. Or do we? Implementing and running the described system would work, but it would work extremely slow. During learning, thousands of calls to the model are made for complicated examples, with each call taking up to 10 seconds. Even if the calls should be instant, the combinatorial number of queries for the given examples quickly blows up the search space. But why does it make thousands of calls? Flashfield performs a soundness check. If the witness functions give some possibilities for the arguments of an operator, we want to make sure that the combinations of these possibilities actually return in a valid program. This is especially relevant for queries, because rather than an intersection over different examples, queries are built from their union. We then need to know exactly what each query outputs to build a sound program. To solve this challenge, we simply don't execute any queries during learning. If a semantic operator is invoked, we use the query as a lookup table for what GPT-3 should have answered. As an added benefit, the learning program is not sensitive to the actual output of GPT-3, as it can never make a mistake during learning. A second challenge arises when we are given many examples, especially in difficult programs, and each example results in multiple possibilities for the output of a query. We are still assuming that GPT-3 is an oracle, so before ranking, any of these combinations has the same probability of being correct. Looking at the queries, however, we can see that some combinations are far more likely. We cluster the outputs of the examples that make up the queries and only keep the ones that are similar enough. Finally, we can get to some results. The first results are not using FlashGPT-3 yet and served as a sanity check, where we compare GPT-3 with Flashfield on a subset of Flashfield benchmarks. Each pair of bars shows how many examples these systems require. We can see that GPT-3 is still able to solve quite a lot of programs, but it requires significantly more examples. The syntactic component is just very important in practice. On the benchmarks with semantics, we see that GPT-3 solves many cases, but with a lot more examples. When FlashGPT-3 requires the same number of examples, the bottleneck is the semantic operator requiring more examples than are required to learn the syntactic part, which typically happens after 2 examples. On the single case where FlashGPT-3 requires more examples, the targeted queries for 2 semantic operators do not contain enough context for the model to know what it has to do. In other cases, making targeted queries decreases the number of examples that GPT-3 requires. By showing the number of calls that would have been made during learning, we can also see that delayed execution and clustering are important. Clustering brings down the number of potential calls, and this makes the search space a lot smaller, and delayed execution makes sure that none of these calls must actually be performed. Finally, these semantic operators are not limited to string transformations. For example, the Flash profile algorithm learns patterns that capture or profile a set of strings using deductive backpropagation and string-to-integer functions. Our semantic position operator is also a string-to-int function, which can extend this functionality to learning semantic profiles. In this example, the model then distinguishes between colors and carriers, something that's hard to do using only syntactics. In the future, we want to explore more of these implementations in other domains, like profiling and code refactoring. We also want to try and shed some light on the black box that is GPT-3, by at least predicting whether an answer it gives could be correct or not. Finally, we want to exploit the generative capabilities of GPT-3. After learning a program to turn sentences into exercises, we then aim to find suitable sentences in books to generate educational material for students learning a new language.